All right, we are looking at Appendix A. It is all the way in the back of the book, behind like page 1185. We're looking at page A2. Page A2, Appendix A. All right, to begin with, on A2, they give us some bold print terms: integers, rational numbers, irrational numbers, but they don't really define for us what those are. So I pulled out our diagram from last year that I thought might be a great review for us of our complex number system. Remember, a complex number is anything that can be written in the form of a plus bi. So that includes both real numbers and imaginary numbers. In an imaginary number, the b value is not equal to 0. So, for instance, if b was 2, I'm going to get something like, if it was negative 2, something like 3 minus 2i. Or if it was positive 2, I might get something like 0 plus 2i, or so just a positive 2i. If, however, that b value is 0, that imaginary component drops out, leaving me with just a real number. Now, real numbers can be subdivided into rational and irrational numbers. It's almost easier to see what a rational number is not. So let's look at the irrational side. If something is not rational, it's irrational because it has two characteristics. It must be both non-repeating and non-terminating. Non-repeating and non-terminating. So for instance, pi never repeats itself, it never stops, so it is irrational. But if you had 1/3, even though 1/3 never stops, it does repeat, so it would have to be a rational number. It has to have both characteristics to be irrational. Once we look at a number being rational, we can break that down even further. So let's start in the center of these concentric circles. A natural or a counting number, those are the numbers we learn when they're a little kid learning to count, 1, 2, 3. If we add on to that 0, then we get our whole number. So every natural number is also a whole number. That's why it's inside the whole number circle. We're just adding 0 on. Then for integers, integers are positive or negative whole numbers. So here's our whole numbers, and then we're adding in the negative whole numbers over here. So integers are just positive or negative whole numbers. So all of the natural numbers are included in those integers there. You can see all the whole numbers are included. We're just expanding it. So then we get to our rational numbers. Root word of rational is ratio. So any number that can be written as a ratio or as a fraction is going to be a rational number. So that throws in our fractions, our decimals, even some of our radicals. It's our whole numbers, because you can take 3 and put it over 1 and it's a rational number. So again, anything in these interior circles are also rational. The only thing that is not rational is something that is non-repeating and non-terminating. So now that we have those bold print terms, we understand a little better their definitions on page A2. Bottom of page A2, they remind us that when you're working with a number line, sometimes called a real number line or a coordinate line, when you're working with a number line, each of the points on that line you could represent with a coordinate. You've got your 0 value, that's the origin, and when you look at two values on a number line, you can compare them or order them. Like 0 is less than 3, but 3 is greater than 0. So we could write that both ways, and we could put them in order from least to greatest and greatest to least. They also remind us of some notation from geometry on page A3. In bold print terms, they give us set, element, union, intersection, set builder notation, and some symbols. So if set A were made up of the integers 1, 2, and 3, and set B were made up of the integers 3, 4, and 5, then we could find the union of set A and B. Union just means to unite them, to put them together. So it would just be 1, 2, 3, 4, 5. I don't need to write 3 twice. Whereas this symbol means intersection. So if I'm trying to find the intersection of A and B, think of an intersection of two roads. It's where they cross over. It's where they overlap, right? So where's the only place that sets A and B intersect or overlap? Yeah, 3. So the intersection of A and B would be 3. Now, if by chance set B had not had 3 in it, so it just had 4 and 5 in it, when they asked me for the intersection of A and B, there wouldn't have been anything. So the way that I represent that is with a null set or an empty set, either of these notations. Also, when I say that 3 is in set A, that means that it is an element of set A, and the way that I could write that is I could say 3 is an element of, that's what this symbol means right here, 3 is an element of set A. Some more notation that we use is set builder notation. And set builder notation just gives me another way to read set A. So what we have here is A is the set of x such that, this line right here is read such that, x is an integer and 0 is less than x is less than 4. So what we're saying is x is between 0 and 4 and it's an integer. The only integers between 0 and 4 are 1, 2, and 3. That's exactly what we had in set A. So that's our set builder notation. Bottom of A3, they remind us of interval notation. Last year, remember, we worked with interval notation, open and closed intervals. They give us quite a few examples on the top of page A4, but here's just a couple of examples for you. Remember that if you have greater than or less than, you're going to use a parenthesis for that. In lower levels of mathematics, you would have used an open dot for that. In pre-cal, we were using a parenthesis last year, and we'll continue that this year. So, for instance, if you had -1 is less than x is less than 2, if you graph that in lower levels of mathematics where you would have put open dots, last year we started putting parentheses for our open intervals in our open interval notation. The great thing about that is the way that I write that in interval notation looks like the way that I graph it. I just have a parenthesis for -1 and a parenthesis for 2. This is a parenthesis at -1 and a parenthesis on 2, and I'm shading in between, showing it's the values in between those two. If instead these were changed to less than equal to, anytime you have less than equal to or greater than equal to, you're going to use a closed dot in lower levels of math. We use a bracket for that in pre-cal and calculus. So where we would have graphed it this way before, notice that we're just putting brackets in the place of those closed dots. And again, our interval notation mimics our graph. So bracket at -1 and at +2. It is perfectly fine to have a mix of brackets and parentheses. So, for instance, if I have x is greater than or equal to -1, I'm going to have a bracket with the -1, but I will always use a parenthesis with infinity or negative infinity. The reason for that is I only use a bracket when I'm equal to something. You can't equal infinity. You can't walk up and put your finger on it and say this is what I'm equal to. It's a symbol that represents the concept of something getting infinitely larger without bound. So we will always use a parenthesis with infinity or negative infinity. Okay, so on the bottom of page A4, we want to look at solving inequalities. And we start with a linear inequality. You're going to solve a linear inequality the exact same way that you would an equality. It's just as if you had an equal sign there. There's only one thing that I have to watch out for, and that is I have to reverse my inequality sign when I multiply or divide by a negative. So if this were my linear inequality, I could go through and I'm going to get all of my x's on one side. So I'm going to subtract 7x from both sides. And then I want to get all my numbers on the other side, so I could subtract my 1 from both sides. Now, how do I get x by itself? Yes, divide by -6, and yes, perfect. When you divide by the negative, you must reverse the inequality sign. I'm going to write that fraction in lowest terms, and if they want interval notation for that, which they typically will, if x is greater than a -2/3, then that's going to be my lowest value for the left side of the interval, going off to positive infinity for my right side of the interval. This was just greater than, so a parenthesis there, always a parenthesis with infinity. All right, example 2 is a combined inequality. It's exactly what it sounds like. I'm combining two different inequalities. So if you want to, you can break that apart into two separate pieces with and in between, and then when you're done, put that back together again. Now, both of these inequalities I could also do on the calculator. Not necessarily the greatest way to do it, but for this linear inequality we were just working with, remember the answer we got was all the values greater than -2/3. So if I typed that into y equals on my calculator, that's exactly what it's going to give me, all the values greater than -2/3. I just would have to do an awful lot of zooming and tracing here to figure out what that value was. And I'm going to have a hard time, especially because this was just greater than, knowing where that stopping point would be. By the way, this symbol, if you're not sure where to find your less than, it's in your test menu, so second math to get to your test menu. So in any case, we had said we could break this into two separate pieces and put and in between. You must put it back together again if you choose to break it apart. So I'm going to go through working on the left-hand side. I'm going to add 2 to both sides and divide by 3. And then, feels like deja vu on the other side, add 2 and divide by 3. And put that back together again because I chose to break it apart. So interval notation for that, because this was equal to, I'll put a bracket with the 2. Because this was less than, I'll put a parenthesis with the 5. And again, I could throw that into my calculator if I want to. So I'm going to throw this in exactly as it looks here. So when I put that into my calculator, 4 is less than or equal to, again, I got that from the test menu, 3x minus 2. And I just got from my catalog. To me, that's the fastest, easiest way to get to it. So that's second 0 to get to the catalog. It's in alphabetical order, so and's pretty high up on the list. 3x minus 2, the less than came from my test menu. And so the answer that it gives me, you can see here, it is between 2 and 5. So again, not necessarily the fastest, easiest way to do this, but it is nice to have a way to spot check that combined inequality. What we will spend a lot more time on this year is polynomial inequalities and rational inequalities. We'll see those more often than linear. So a polynomial inequality, like this one is a degree of 2 and this one's a degree of 3, I'm going to have to build a sign graph for those. So I'm going to set it equal to 0 and solve it to get my critical numbers to go on my sign graph. So I factored this and set each of the factors equal to 0, and I plotted those critical numbers. Now I need to figure out where this is positive and negative, and I'm going to pick a test point to do that. So 0 for me is my favorite value to choose when I can. So I'm going to choose 0 as a test point, so I plugged that back in, 0 squared minus 5 times 0 plus 6. So 0 squared minus 5 times 0 plus 6 gave me a positive 6. The 6 is really irrelevant. The fact that it's positive is what matters, because each of these critical numbers divide my number line up into intervals. So I have an interval right now from negative infinity to 2, and then an interval from 2 to 3, and then an interval from 3 to infinity. Every value in the same interval will have the same sign. So when I test one point in that interval and find out it's positive, that means that every single value from negative infinity to positive 2 is going to be positive. All right? Then I could test a point in this interval from 2 to 3, and I would get negative. Then I could test a value in the interval from 3 to infinity, any value in there I want, and it would be positive. So what we learned last year was the rules that go along with critical numbers, and we found out that at every single critical number, we'll talk about double and triple and quadruple in a minute, but at every single critical number, your sign's going to change. So if I know that rule, instead of having to test every single interval, I'll know the sign's going to change here, and I'll know the sign's going to change here. So now I've got my sign graph, and I'm ready to answer the question that was asked. They asked me, where is this less than or equal to 0? What kind of numbers are less than 0? Yes, negative. So we're looking for where this thing is negative or equal to 0. So if I look at my sign graph, that's just this little piece right here where it's negative and it's equal to 0 at 2 and at 3. So I'm going to say all the values between 2 and 3, including 2 and 3, right? So equal to gives me a bracket, so bracket at 2 to 3 and a bracket with the 3. Now, if I throw this into my graphing calculator, so I type in y equals x squared minus 5x plus 6, it generates this graph. We can understand then why the sign graph does what it does. We said that it gave us an interval from negative infinity to 2 where everything would have the same value, positive or negative. And sure enough, from negative infinity to 2, all of those values were positive. Then the next interval from 2 to 3, they would all have the same sign. Yep, from 2 to 3, all those values were negative. And then from 3 to infinity, all of them would have the same sign. All of those were positive. Instead of having to take the time, though, to build the whole graph when all I really need to know is just where it's positive and negative, that's where the sign graph can help me. I don't have to actually be precise and find out what all the y values are. I just need to know if they're positive or negative. And the sign graph tells me that, so it saves me some time and some effort. So looking at this graph, I can see that it actually was less than or equal to 0. Less than 0 would be below the x-axis, equal to 0 would be x-intercepts, intersecting the x-axis. So sure enough, that was from 2 to 3, and I was equal to 2 and 3. And that's exactly what we got from our sign graph. Now, if you're on a portion of a test or a quiz or an AP exam where you have your graphing calculator and they ask you this, I don't need to do any of this, right? All I'd have to do is throw it into y equals and look at the graph to see, okay, it's below the x-axis from 2 to 3, and it's equal to 0 at 2 and 3, and I could go straight to that answer, right? So work with what we're given. Look at the next one. For the next one, we've got x to the third minus x squared is greater than 0. Oh, let me back up 1 second. In our textbook, we have that little Ghostbuster icon that's basically don't do this. This is the most common mistake that students make. I'm going to throw one of my own in here and say that same thing. The most common mistake that I see on a polynomial inequality is you factor it, but then you try to keep that less than or equal to, and so you try to say this is your answer, and you can see that it's definitely not the same thing as what we just got. You have to make a sign graph or it won't work. Okay, so for our cubic inequality, we're going to start the same way. We're going to set it equal to 0 and solve it just as if it was an equality, and those solutions that we get are our critical numbers. But this time, we got a double root of 0 because x squared equals 0. That's like x times x equals 0. That's like getting x equals 0 as an answer 2 times. That matters. So when I come over here and I plot my critical numbers, I'm going to make a note for myself that that is a double root. So when I go to find a test point, I can't use 0 since it's one of my critical numbers. It wouldn't do any good. So I'm going to use a -1. So I plug -1 in, -1 cubed minus -1 squared. -1 cubed minus -1 squared. I get a -2. The 2's irrelevant. All I need to know is that it's negative over here. We said that your sign would change when you cross a single critical number. This, however, is a double critical number. So what's going to happen is, as I hit that first critical number, it'll change from negative to positive, and when I hit the second one, it'll change from positive back to negative again. It will change twice, so it will appear to not change at all. This, however, was a single critical number, so it will hit that and change one time. So the short version of that is, if you have an odd number of roots, a single root, a triple root, so 1, 3, 5, 7, something like that, then your sign is going to change. If you have a even number of critical numbers, like a double root, a quadruple root, something like that, your sign changes multiple times, but it's going to appear to not change at all. The sign is going to stay the same on your sign graph. All right, so for this one, we wanted to know where it was greater than 0. What kind of numbers are greater than 0? Yeah, positive. So we were looking for the positive piece over here. So that would be the values that are greater than 1. So interval notation for that would be 1 to infinity. And sure enough, if we throw that into our calculator and we look at the graph, if we're only interested in where this is greater than 0, then yes, that is only the piece where x is greater than 1 and going to infinity. All right, last one that they give us here is a rational inequality. And the main difference is that you have to set your numerator and your denominator equal to 0 with a rational inequality. So when I do that, I set the numerator equal to 0 and get -1. I set the denominator equal to 0 and get +2. Can your denominator ever equal 0? No, right. Where your denominator equals 0, your function is undefined. So I'm going to make myself a little note here that I can't actually equal that value, and I'm even going to make myself a note on the graph so I don't accidentally include it in my answer. So I've got my critical numbers. I'm going to pick a test point. I went back to 0 this time, and I got a negative value. Cross a single critical number, the sign will change. Cross a single critical number, the sign will change. So there's my sign graph. We want to know where this is less than or equal to 0. So less than is negative, and then equal to 0. So we're looking for where it's negative or equal to 0. That's this interval right here. So we're going to choose that interval from -1 to +2. Now I have to be careful because this is less than or equal to. I naturally want to use brackets here. I do use a bracket with the -1. Do I use a bracket with the +2? Right, I do not use a bracket with the +2. We made ourselves a note here. I can't be equal to it. I can't be equal to it. I don't care what this says. If I use 2, I'm going to get 0 in the denominator, and that's undefined. I cannot be equal to it. I can only use a parenthesis there. And when I graph this, I understand why that's the case, because there actually ends up being an asymptote at positive 2. So yes, I do need to indicate it on my sign graph as a critical number, or I'll miss that sign change at that asymptote. But I don't want to include it as part of my solution because my graph is not equal to 0 there. It is negative or equal to 0 going up to the number 2, but it's not included in it, so I don't want a bracket there. All right, so here's our homework for tonight. Notice that I'm only giving you odd problems so that you can check the answers in the back of the book. So please check before you come in tomorrow so you know what you have questions about and what you don't, so that we can take questions and put those up on the board, and you know the ones that you can volunteer for because you've gotten them right. Also notice that this is every other odd. So if you have a question about what we mean by every other odd, we'll do that frequently this year. That is if you listed the odds starting with 13. So 13, 15, 17, 19, 21, 23, so on. That means you're going to do 13, omit 15. Do 17, omit 19. Do 21, omit 23. Okay? Every other odd.